Okay, so welcome to our Wednesday session. I have received responses from several of you with the homework. I haven't had a chance to pull it down yet. So what I'm going to do is share with you the answer key and let you compare that with your answers. And if there aren't any questions, then we will move on. So I'm going to pull out the ones that I had put on the assignment that were basically the density questions. So here are the density questions. Let me share this screen. Do you all see the where it says the density of mercury? Yes or no?
Yes, we can see it.
Okay, great. All right. Before I go on though, let's see who we have in class today. Let me go and see who we have in class. Okay, Lex and Kaylin, Keston, Kendra, Lanisha, Nigel, okay? Thank you all for being here on time. I hope you all have all signed in for today's lecture. Okay, so look at the answers here for number 1. The density of mercury was given. What is the mass of this volume sample? Did you all get that answer? Does that answer look correct? 2.94 kilograms? I'll give you a minute to pull up what you worked on and see what answer you received. Okay, so I haven't had a chance to look at your answers, but if you have what you sent to me, just pull that up and see if the problem that was about the density of mercury, these are not numbered the same. I took these from the author's exam with test questions, and I gave them to you as an assignment. So the numbers may be different, but you should have the same problems.
Yeah, it's question 5.
Okay, so did you get this answer for question 5?
Mm-hmm.
Okay. Anyone else? Question 5, this should be your answer. If you didn't get this answer, let's discuss it. If not, we can move on. Okay, so I'm assuming this is question 6. Is this the answer you got for number 6, class? Okay, does that answer close to your answer for number 6?
Yeah.
Okay. How about number 7? I think we did that one in class, didn't we?
I don't think we did this one in class. We might have, but no, we didn't do this one.
Okay. Did you all get this answer for number 7?
Yeah.
You got that answer? That looks correct. Okay, so you know how to do it then. Okay. How about number 4? Did you get that answer?
Mm-hmm.
Okay, very good. How about number 5? Does that answer look correct?
Can we do that one?
Yeah, I got that answer, but it was kind of weird. So can you explain the details of it?
Okay. Let's look at this one together. All right. So it says the average density of the material in the intergalactic space is approximately, they gave us the density. We know it's density because of the units. So let's see what it's asking us to do. Let me put my pencil out here. Okay, hold on. I'm trying to get my pencil to write on this paper. Hold on. Okay, class, I had to go and try to find some way to write on the screen because for some reason, my menu that allows me to go back and forth between my pencil is missing. So let's see. The average density of the material in the intergalactic space is approximately. So this is the density for the intergalactic, whatever that is. And it is 2.5 times 10 to the minus 27 kilograms per cubic meter. What is the volume of a lead sample? So this is then they gave us the density for the lead sample. And they said that that is 11,300 kilograms per meter cube. Okay, so what is the volume of a lead sample that has the same mass as, so they gave us the mass of the intergalactic. So the intergalactic mass is oh no, this is meter cubes. So they gave us the volume then. They're looking for the mass. See, this is volume, but it's not kilograms, it's what? It's meters cubed. So it says, what is the volume? What is the volume of the lead what is the volume of the lead sample that has the same mass as the intergalactic space? So we have the mass, we have the volume of the, hold on. So I don't even have any eraser anymore. Right, mark through this. So this is the volume of the intergalactic space. So from there, we can find the the mass of it. So they're asking us then to find the volume of the lead sample. So if we know both the mass of the intergalactic space sample, and we know the volume, we're going to compare these two. So the thing you want to know is that this is the average density of the material intergalactic space. So our equation says, my pencil's not working again. What do you all see on your board? What do you all see? Please tell me.
The homework questions.
Okay. So is it moving up and down like this?
Yes, ma'am.
Okay. I'm trying to write, and that's why it's doing that. It's not allowing me to write on the screen. Okay, let me go to my whiteboard and see what happens. Hold on. New share. Okay. All right, now I finally got my screen to work. What do you all see now? Do you all see the whiteboard?
Yes, we see it.
Okay. Okay, so we were given the density of the intergalactic space, and we were given the volume of the intergalactic space. And from there, of course, we can find the mass of the intergalactic space. And then we were given the density of the lead, and we're asked to find the volume of the lead, and we need to know how these two relate so we can find the mass of the lead. Okay, let me go back now that my pencil is writing. Okay, so they want to know what is the volume of a lead sample that has the same mass. So that means we got to first find the same mass. So what is that same mass that's asking us to find? So first we have to find the mass of the intergalactic piece, right? It says the same mass. So the mass that we're going to put over on our whiteboard will be the mass that was in the intergalactic space material. So let's do that first. See if I can move this down some. Okay. All right. So, oh goodness, my pencil is gone again. Okay. So we know that the equation for density is mass per unit volume. And this implies we can find the mass if we know the density and the volume, which we know. So we have our density is 2.5 times 10 to the minus 27. Is that correct? Yes. Kilograms per meter cubed. And our volume is huge, okay? 8 times 10 to 24 meters cubed. So meter cube and meter cube will cancel, and we'll have our mass in kilograms. So we multiply that out. We got 2.5 times 8. What is that? That's 16 plus 8. 16, what is that? 24? Is that 24? 2.5 times 8. What's that, class? 24, right? Yes. Oh, I'm sorry, 20. Half of 8 is 4. Okay. So we get 20, right? So we have 20, 2.5 times 8 times 10 minus 27 and positive 24 will give us a minus 3. Minus 3. This is grams. So this is our new mass. In other words, this is the mass. It says it has the same mass. So now we know the mass of our lead. So now we can find our volume. So now let's go up here and say, okay, I know that density is mass over volume, and that implies that volume is going to be what? Volume is going to be what? Mass divided by what? Density, right? So now we know our mass. Our mass is 20 times 10 minus 3 kilograms. And our volume, the volume of lead, it says is 11,000. Let's write this in scientific notation so it'll be easier to do. So let's just say 11.3. 11.3 times 10 to the what? Third, right? Let's do it like that. And this is a kilogram per. So per means it's going to go to the top, per meter cube. So kilograms and kilograms will cancel out. So now we've got 20 divided by 11.3. So 20 divided by 11.3, and we get 1.76. So we get 1.76 times, we have 10 to the third in the denominator. So when it comes up, it becomes a -3. So a -3 times -3 will give us a -6. So we get 10 to the minus 6, and we have our volume in meters cubed. So 1.76 times 10 to the minus 6. So they rounded that up to 1.8. So that's why our answer is 1.8. All right, does that answer your question? Does everyone understand it now?
Mm-hmm.
Okay. All right, so the key thing there was, what is the volume of a lead sample that has the same mass as this intergalactic space sample? So once we found how much mass that was, that's the same mass they want us to use for our lead sample. Okay, so those are the type questions that you will have in our next exam or assignment for chapter 11. Before I move to chapter 12, I wanted to do just a few more problems with pressure. Since most of these dealt with density, I want to do some with pressure. So let's go to the assignment I sent you just before we came online. Okay, so here we have another assignment, only 4 problems, and we're going to just look at some of these kind of quickly. But what I want to point out is something that I failed to put on the equation quiz, but you can add it to your notes. And I want you to know, because you hear this term 1 atmosphere. So when you hear the term 1 atmosphere, I'm having the hardest time with this thing today. I don't know why it's not allowing me to to see my, okay, let me go to, let me share, hold on. Okay, for some reason, whenever I go to this board now, I cannot see how to pull my pen up. And that is causing me a problem because I have to be able to write on the board and it's not showing me my pen. Hold 1 second. Goodness, hold 1 second. Okay, class. I'm sorry about that. Okay. All right. So when you hear the word atmosphere, one atmosphere, you will see that written as 1 ATM. That stands for atmosphere. And 1 atmosphere is 14.7 pounds per inch square. What does that mean? In our atmosphere, the average weight of the air that sits on 1 square inch is 14.7 pounds. So that means that in our atmosphere, where we are here on this earth, we have an average value that we use that says that 14.7 pounds of air sits on every square inch. And that is equivalent to about actually the exact number is 1.013 times 10 to the 5th pascals. Remember, a pascal is a Newton per meter square. So you can see that a pascal must be a very small number since it takes almost 10 to the 5th of them just to equal 1 atmosphere. And 1 atmosphere, we say, is 14.7 pounds. So somewhere in your notes, please make note of that. So you will have those conversions in your head. So the question says, how much force does the atmosphere exert on one side of a vertical wall 4 meters high and 10 meters long? So the first thing we know is, if we know the dimensions of the vertical wall, then we know the area. So first we find the area, and the area is 4 times 10, so that's 40 meters square. That's my area. And it says, what is the force? So we want to know how many newtons. And how much force does the atmosphere? So the atmosphere has a pressure of 1.013 times 10 to the 5th pascals. That's what we start with. So our equation says that pressure is defined as force over area. So this implies that my force must simply be my pressure times my area. And therefore I have my pressure, which is atmospheric pressure, which now I've given you as 1.013 times 10 to the 5th pascals times my area, which is 40 meters squared. And remember, a pascal itself is, a pascal is what, class? A Newton per meter square. So that will cancel out. And my answer will be in newtons. And when you multiply that out on your calculator, you get 40 times 1.013, and you get 40.5, 40.52. So then, let me move this down. Hold on 1 minute. I can't move it down. I'll just erase it in a minute. I can't move this down anymore. I don't have control of my screen anymore, so I'll figure that out later. So then my force, we get 40.52 times 10 to the 5th newtons. But of course, they want us to write this number in scientific notation, as we can see here. So that means that this has to get smaller by a factor of what? 10. So that's 4.05. And this has to get larger. So it's 10 to the what? 6. This part of the number gets smaller. This part of the number has to get what? Larger. That's my answer. So that would be answer D. Okay? Answer D. Now, let's look at one like number 2. Well, number 2 is kind of easy since I've given you the atmospheric pressure. Now, he says here to use 1 times 10 to the 5th, although the exact value that you want to use in most calculations will be 1.013. But this is a good estimate because there's a 0 there, so that's a good estimate. Okay, let's move down to the next problem. In a classroom demonstration, a 79.2 kilogram professor lies on a bed of nails. The bed consists of a large number of evenly spaced, relatively sharp nails mounted in a board so that the points extend vertically outward from the board. While the professor is lying down, approximately 1,950 nails make contact with his body. What is the average force exerted by each nail on the professor's body? So the average force. Now, first of all, they gave us his mass. So from his mass, of course, we can find his what? His weight. And the weight is a what? A unit of force. So we find his weight. And then once we find that force, it says what's the average force on each nail. So the average force per nail would be his weight divided by how many nails we have. Okay, so first let's find his weight, and then we'll find the average force. So we have his weight then is 79.2 times 9.8, and this will be newtons because we're going to have kilogram, meter per second squared. That's going to give us a newton. So now you don't have to write that down every time because you know the unit is newtons. So we get 79.2 times 9.8. So we get 776.16 newtons. Now, the average force would be that number, 776 newtons, divided by the number of nails, which is 1950. And that would give us the average force. So what do we get? Divide that by 1950. And I got 0.398. So we get, okay, so we get answer B, 0.398. Okay. Now, if the area of contact at the head of each nail is this many meters square, so now we know what? We know the force per nail. We know the contact area per nail, which is the area. What is the average pressure? So we're going to find pressure now by saying what? Force over area. So please do that. You should get one of these answers. I only gave you 4 problems. 1, 2, 3, 4. Okay. All right. So now I want to move from that and go to our next topic. Our next topic is in chapter 12. So this is a very quick chapter. I hope we can get it in 30 minutes. Okay, so let's go down to number 16. Okay, number 16. I want to write these in for you very quickly. But first of all, before I do that, I want to go back to just a visual, give you a visual. Okay, so let me remind you of something. We have temperature scales. So the common one for us is the Fahrenheit scale. So this is the degree Fahrenheit. And we have what we use now is going to be the freezing point and boiling point of water. So my substance is water. And who knows what is the freezing point of water? So many degrees Fahrenheit. Who knows what that is? Write it in for me. If you know what the freezing point of water is, give me that number in chat. At what temperature does water freeze on the Fahrenheit scale? Okay, Kaylin, very good. 32 degrees Fahrenheit, water freezes. And what about the boiling point of water? So this is the freezing point. We bring it all the way up to the boiling point. Okay, on the, very good, Keston, 212 degrees Fahrenheit. So this is the freezing point for water, and this is the boiling point for water. Now, let's move over to degree Celsius. What is the freezing point for water on the Celsius scale? Water freezes. What? Okay, very good, Keston. 0. Okay, 0 degrees Celsius, water freezes. And what about the boiling point on the Celsius scale? Okay, very good. 100 degrees Celsius. So now you can already see why the Celsius scale is the Celsius scale is the SI scale. The Celsius scale is the SI unit. In other words, we have to be able to think now about temperatures on the Celsius scale. So we have to be able to convert between Celsius and Fahrenheit, because most of us think of temperatures on the Fahrenheit scale, but now we have to be able to also be able to convert in our minds to the SI unit. So what we see here clearly that there are 180 units between freezing and boiling on the Fahrenheit and 100 on the Celsius. The main thing we notice though is that on the Celsius scale, it begins at 0. On the Fahrenheit, it begins at 32. So now our conversion will not just be both beginning at 0 as it has always been in the past. So, but I'm sure you had this in high school, but I want to explain to you where it came from. So then the ratio is 180 to 100. If we reduce that down to its simplest form, we would end up with 9/5. So that means that this number, 180, is 9/5 greater than this number. Plus we have to add what? 32 to our beginning point. So the first thing in chapter 12 that the author wants to point out then is how to convert between the temperature scales. So I'm in chapter 12, and the first thing he gives you is this equation. Now, sometimes you may see this written in the form of a fraction. Sometimes you may see it written in the form of a decimal. I prefer a fraction. I prefer the 9/5, and I think that you will too when you see how much easier it is to convert between one and the other. So our first equation then that we have on this sheet, I'll go back to my sheet now. Okay, so I said convert Celsius to Fahrenheit. In other words, I want the temperature to be, hold on, let me find my pen. I want my temperature to be temperature Fahrenheit from temperature Celsius. And we already saw that it's 9/5 greater than temperature Celsius. And we have to add the what? The 32. So temperature Fahrenheit is 9/5 temperature Celsius plus 32. And then that would be in degree Fahrenheit. That's my unit. So let's give an example. And these are very, very straightforward equations. Does not require any difficult math. So I saw a problem that I want to use as my first example. And I'll go to the whiteboard and we'll do that one very quickly. Okay. All right. So the example I have is this one, very easy. In 1983, a temperature of -89 degrees Celsius was measured at a Russian station. So this was my what? Temperature Celsius. And I want to know, what is that temperature on the Fahrenheit scale? Okay, so we know that temperature Fahrenheit is going to be 9/5 temperature Celsius, which is -89. Okay, just putting in a number like that. Then plus what? 32. So first we have to find this number, which is going to be negative, and then add this number. So we have -89 times 9, divide 5, and that gives us -160.2, and add that to 32. So when we do that, we get -128. And then we're going to say what? Degree Fahrenheit. That's how we do it. Okay? So -89 degrees Celsius is equivalent to -128 28 degree Fahrenheit. That's very, very, very what? Cold. When you agree that's very cold? And that was a temperature that was recorded at a Russian space station in Antarctica. All right. Now, while I'm here, let's take our equation and write the second equation. But I want to use this to point out a common error that students make when they're solving this next problem. So let me point that out by showing you this equation. So our first equation says temperature Fahrenheit is 9/5 temperature Celsius plus 32. So I want to get temperature Celsius by itself. That means that I can write this now as 9/5 temperature Celsius. This is a term that I'm adding to temperature Celsius. So it goes to the other side and becomes negative. So I have minus 32. Now I want to get temperature Celsius by itself. So that means I must multiply the other side by the reciprocal of this number. This number is 9/5. Its reciprocal is 5/9. So when I multiply 5/9 on the other side, be very careful to put the parentheses first because I'm multiplying 5/9 by everything on this side. And for some reason, students like to just make it 5/9 times temperature Fahrenheit. I have seen this so many times. Let me show you what I see all the time. I see temperature Celsius, and I see 5/9 temperature Fahrenheit minus 32. That's what I see so often. And that is not correct. It has to have the parentheses. Okay? So therefore, this is my second equation. Please make sure you note that it has to be what? Parentheses. Okay. Okay. So our next equation then is convert Fahrenheit to Celsius. So temperature Celsius, we say, is 5/9 temperature Fahrenheit minus 32. And then that will be degree Celsius. So now let's go and do some common temperatures that, well, let's just do water first, since we know what the answer should be. Let's just do water, and then we'll do another one. Okay, so let's take water. We know that water boils, the temperature on the Celsius scale is 100 degrees Celsius. And I want to know, what is that temperature on the Fahrenheit? We know what it is. We're going to make sure we understand how to solve the equation. So we say temperature Fahrenheit. I'm looking for the other way around. I'm sorry. I'm going to do this. I'm trying to get Fahrenheit, which is 212. And I want to solve for temperature Celsius. Okay, so temperature Celsius, we say, is 5/9 temperature Fahrenheit, which is 212 minus 32. So what do we do first? First, we take 212 and subtract what? 32. So we got 212, and we subtract 32, and we get what? Of course, we get 180. So we have 5/9 of 180. And of course, we multiply by 5. And we divide by what? 9. And of course, we get what? 100. So we know then how to convert. Now we're looking for what? Temperature Celsius. So therefore, we put what? Degree Celsius, like that. Okay, now let's take one that we know. Okay, let's take this one. We know that the human body has a normal average temperature of 98.6. 98.6. Every time I go to the dentist, before I can have any work done because of this COVID-19, she has to take my temperature. And it's amazing how every time my temperature is about 98.6. It's like I have a very normal body temperature. So what is that temperature on the Celsius scale? That's one of the numbers I want you to recognize. Okay, so let's do that. Okay, so now my temperature on the Fahrenheit is 98.6. So I say 98.6, and I subtract 32. That's what I get. And then I say times 5 and divide 9. And I do all that and I get 37 degrees Celsius. So now I want you to recognize that 37 degrees Celsius is normal body temperature in SI units. So when you see 37 degrees Celsius, you will recognize that. The other one I want you to recognize, I want you to do it for me real quickly now. What is room temperature on the Celsius scale? I want you to give me that. So first of all, I'm just giving me an approximate number. In other words, you're in a comfortable room. The room is very comfortable to you. That's room temperature. So what do you think room temperature is on the Celsius scale? Give me a number you think it is for Fahrenheit first. What's a comfortable temperature for you in a room on the Fahrenheit scale? Someone? Okay, someone said 70. 70 feels comfortable. Okay, let's just go with, somebody said 75, somebody said 70. Just go with 72. Okay, let's go with 72. So now, what is that temperature? What is that temperature on the Celsius? Okay, give me that answer. I want to convert 72 Fahrenheit into Celsius. What will be that number? Okay, Kaylin, very good. Okay, approximately 22 degrees Celsius. So if you ever given these numbers, now you have a good feel for the various numbers on the different scales. If you see 37 degrees Celsius, think about normal body temperature, 98.6. If they said it's about 22 degrees Celsius, that's a nice room temperature. If it just said 22 degrees, you'd be thinking, wow, that's freezing, unless they say what? Degrees Celsius, then you know that's room temperature. Okay, so that's what we want to cover there. Back to our chart. The other temperature scale is called the absolute scale. Now, this scale is very critical when you come to your gas laws. I'm going to try to cover a few of the gas laws. So it's called temperature Kelvin. It's a Kelvin scale. And it is simply the temperature Celsius plus 273. That is, now your author may have put 273.1. Let me look and see what he put. You can put 273.15. Okay, let's see what you have to put 0.15. We put it there. Okay. Now, the thing about the Kelvin scale is that we do not put a degree symbol. So one way that you know you've learned your physics is that when you write the Kelvin temperature, you simply use an uppercase K and you do not put the degree symbol. All right. So let me give you one problem and let's see who can give me the answer first. Let me give you a sample problem. I'll give you a couple very quickly, just to make sure you understand this chapter. All right. So the question is, I'm gonna go to my whiteboard. Okay. We know that oxygen has a very, very, very low boiling point. So on the Celsius scale, oxygen boils at negative 183 degrees Celsius. What is that same temperature on the Fahrenheit and then the same temperature on the Kelvin? Okay, so solve that real quickly. Oxygen boils at negative 183 degree Celsius. That temperature on the Fahrenheit scale and that temperature on the Kelvin scale. That's problem number one that you're going to do now. Everybody has to answer. This is for a grade. Then problem number two, same problem but different numbers. Okay, the Celsius equivalent of 120 degrees. So now I'm giving you degree Fahrenheit is 120 degrees Fahrenheit. What is that temperature on the Celsius? What's that temperature on the Kelvin? Okay, so I'll give you a few minutes to work those two problems and then go into chat and give me your answers. Okay, in case you don't have them written down, remember we said that temperature Fahrenheit was 9/5 temperature Celsius plus 32. I gave you a visual to help you to remember that, if you remember the picture that I drew. And then we said temperature Celsius is 5/9 temperature Fahrenheit minus 32. Okay? So those are the two conversions that we have. Well, we have one more. We said temperature Kelvin was temperature Celsius plus 273.15. Okay? So those are the three that we're using. Okay, it looks like Kaylin, Nigel, let's see who else is getting these answers. Kaylin, Nigel, Lex seem to be understanding. I haven't heard from Lanisha. I haven't heard from Keston. I haven't heard from, let's see, Kendra. Now, I want to know if others of you are having difficulty solving these equations. If so, we can solve it together, but I need for you to practice solving it on your own, because you will never understand it unless you actually do it. So I'll give you a minute to write these problems down on your scratch paper. So I did want to cover one more thing in this chapter before we end it today. We're down to 15 minutes. So you're converting negative 183 degrees Celsius to Fahrenheit and Kelvin, and you're converting 120 degree Fahrenheit to degree Celsius in Kelvin. And you can put those answers in later. I'll leave it open for you to put those answers in, but I have to move on to the next part of the lesson. But if you have any questions, though, we'll do this together again at the end of the lecture. Okay, let me go now to our other equation. Okay, so this equation is called the amount of heat transfer. So let me tell you what's going on in this equation. They're simply saying that when we heat something up or cool something down, of course, we're changing the temperature of it. And when we change the temperature of something, that can only be done by adding what we call heat energy or removing heat energy. So the first thing I'm going to tell you is that what is being removed, what is being transferred is energy. And energy, of course, is measured in joules. It's heat energy. So I'm going to show you a picture right here. So this is the picture that I think best explains it. We have a flask with water in it. And we know that water at room temperature, we'll say it's about, I think the author uses 20 degrees Celsius for room temperature. And he has 1 kilogram of water sitting in a flask. Now this flask is heated up. Okay, we put if you were in a lab, you put a Bunsen burner, and it would burn until the temperature changed. And the temperature change you're looking for is just 1 degree. So you have the same flask, and now it's 21 degrees Celsius. 21 degrees Celsius. Oh, it went away. And we've added some heat energy. So what is that heat energy? Well, the heat energy, and the symbol the author uses is Q. So let me put down the equation. Give me a minute to take this off. Whew, this is not good. I don't know how to take this off. Okay, so let me just do it like this. Q, okay? We have to know how much we have, which is the mass. We have to know the change in the temperature, okay? And that is delta T. But one other thing we have to know, class, is what is the substance? Because what we know is that it takes different amounts of heat to raise different materials by the same temperature. In other words, the reason why we cook with, say, metal containers that are copper clad is because copper transfers heat so rapidly. So the way we identify the material is what we call the specific heat capacity, and that symbol is C. So in your textbook, you have a long list of substances, and they identify for you the specific heat capacity. So one item is water. And water has a specific heat capacity that is very common. And we say that that number is 4.2 times 10 to the, let's see what author gives you first in units. Hold on, let me see what units he gives you, because every book is different. Okay, so in your book, he says for water, the specific heat capacity, he said, is 4186. So we're gonna say 4.186 times 10 to the third, which is kilojoules per kilogram for 1 degree Celsius. If you look in your book, he gives you the specific heat capacity for water. What does that mean? That simply means this. If I wanted to raise 1 kilogram of water by 1 degree Celsius, I've got to add 4.186 kilojoules of heat energy. That's what that means. So the best way for me to explain that to you again is with the problem. So I'm going to go to the problem that we have as our example. I thought I had sent that to you, but I'll send it to you. I'll send it to you later. So let's look at a problem, and then we'll be almost through with this chapter. Okay. Okay, let me see, did anybody finish these problems up? Let me see before I erase this. Okay, Keston, the only thing I see here, Keston, is that this temperature needs to be negative because we were given negative 183. So that answer should be negative 297. And then the next part is correct. Okay, I still haven't heard from Lanisha. And let's see, did I hear from Kendra? Let me find Kendra. Didn't hear from Kendra yet. Okay. Make that correction, Keston, and then hopefully Kendra and Lanisha will give their answers. Okay, let's do a problem. I'm going to erase this now. Okay, so let's look at this problem. And this problem is well, it has several parts, but let me go back to my chart. I forgot something. I'm going to go here. So since we said that heat energy is also measured in joules, then we have an equation for power. And before, recall, power we said was energy divided by time. So that means that down here, So energy can be all kinds of energy. We can have kinetic energy, we can have potential energy, we can have rest energy. So we can also have heat energy. So this equation means then that power can also be heat energy divided by time. And of course, the heat energy is in joules. Joules per second, of course, is a watt. So now, with that in mind, I want to show you a problem that was a good example that includes several points that we made in this section. Okay, and then we'll end on that problem. Okay, let me find the problem again. Okay, so the problem says this. It says, how long will it take a 1.2 kilowatt electric kettle? So when they say 1.2 kilowatts, that's the power because it's in watts. How long will it take a 1.2 kilowatt electric kettle to heat 0.8 grams of water? So we have our mass of water is 0.8 kilograms from room temperature. So room temperature for this water is the temperature initial, and that's about 20 degrees Celsius. The author uses 20 degrees Celsius for room temperature. And then it says to the boiling point, Now, let's use the what we just learned. So what we learned? We learned that, okay, and it says how long, so we're looking for time. In fact, it says how many minutes will it take? So the question was, how many minutes would it take to heat this water from room temperature to boiling point? And now we know that the boiling point, the final temperature on the Celsius scale is 100 degrees Celsius. Now we know that. So now we're looking for time. And we just saw that power is energy. In this case, is heat energy over what? Over time. In other words, this is the power consumption. And we want to know how much time it would take to do what? To raise the temperature from 20 degrees to 100 degrees. So therefore, this implies that my time is going to be my heat energy divided by my power. And what is heat energy? My heat energy is MC delta T divided by the power. Now, what is M? M is the mass. What is C? Well, we're heating up water. So therefore, we can write down the specific heat capacity for water, H2O. And that's the one I want you to learn. So for me, you can just round it up to 4.2 kilojoules per kilogram degree Celsius. That is the specific heat capacity for water. Okay. Oops, hold on. Okay. So everything else now. Okay, so what's my time? How much time? Now the time is mass, which is 0.8. Let me ask you, let me point out something right here very quickly. Well, no, let me just do it and then I point it out. Okay, 0.8 kilograms. Okay, mass. Specific capacity is 4.2 kilojoules per kilogram degree Celsius. Delta T. Delta T is 100 minus 20. So that's 80 degrees Celsius. And all of that is divided by the power. And the power was 1.2 kilowatts. Now, let me show you something. We know that kilograms and kilograms cancel. And the reason why you don't want to cancel this K with this K, you could do that, of course, but we still have a K left. So it's okay. I guess you could do it either way, all right? But since we know that the units is mass, this kilogram and this kilogram will cancel. And this kilo and this kilo will cancel. And this degree Celsius and this degree Celsius will cancel. So the units remaining are joule per watt. So you want to make sure that a joule per watt will give you the SI unit of time. In other words, a joule per watt needs to be what, class? Needs to be seconds. So what is a joule? A joule is a what? Well, we'll just say what a watt would be easier. What's a watt? Okay. So a watt is a joule per second. So when the joules cancel out, I just have seconds remaining. So I know that this unit, joule per watt, is actually a second. So now I just need to do the math. So I have 0.8 times 4.2 times 80. I get all that, and I divide that by 1.2, and I get 224. So I get 224 seconds. But the author wants the answer to be in minutes, which is a common time that we use when we're heating up something. We don't count by the seconds, we usually count by the minutes. So of course we divide that by what? By 60, so 60 seconds in a minute, and we get 3.73. So we get about 3.7 minutes. Okay, so I'll send you a few problems to solve using this understanding. Now, the important thing is when you solve the problems, make sure you convert it, or if it's not in Celsius, that you convert it to the Celsius scale. Now, if you have a substance that's not water, you can simply go on the internet and look up the specific heat capacity for whatever it is. Say it's lead. If you don't have your textbook, you may not have that number there. Whatever substance it is, you can just Google it up and that number will be close enough to what the author has used. Okay, with that being said, then we will end here. Do we have any questions?
I'm not getting 224 for my seconds.
Okay, let's see what the answer is. Did you say 0.8? That's 4.2 there. 4.2 times 80 and divide 1.2. Try it again, please. You got 0.8 times 4.2 times 80. And then when you get that answer, divide it by 1.2. What'd you get this time? Did anyone else?
Getting different answers.
You're not getting 224?
No, ma'am, I'm trying again.
Okay, put in 0.8 times 4.2 times 80. And then divide 1.2.
Okay, I got it.
Okay, and then divide that by 60 and you get the answer in minutes. Okay, any other questions? So please also go ahead and use your internet or your textbook and finish filling this out. The heat of vaporization of water, the heat of fusion of water, and the definition of sublimation. Those are important terms for you to know in this chapter. And with that, I have completed this chapter. What we'll do tomorrow is we'll solve a few more problems having to do with amount of heat transfer. We'll do a few more problems with that. Okay, so went over just a little bit. Please go ahead and sign out. And if I don't see any problems in your email, look in your textbook and just find a few to work on, and then we'll do a few in class tomorrow. Okay, y'all have a good evening.